Hi, my name is Kiran Baburaj. Welcome to Career Campus Pro YouTube channel. Today we are diving into one of the most fundamental graph traversal algorithms, depth first search or DFS. DFS is a graph traversal algorithm that explores as far as possible along each branch before backtracking. Think of it like navigating a maze. You go down one path as far as you can, and if you hit a dead end, you backtrack and try the next path. This makes DFS perfect for problems like finding connected components, solving maze, or detecting cycles in a graph. DFS can be implemented either using recursion or an explicit stack. In this video, we will focus on the iterative approach using a stack, which is often more efficient and easier to understand. So let's visualize how DFS works. We start at the root node, mark it as visited, and add it to the stack. Then we pop a node from the stack, process it, and push its unvisited neighbors onto the stack. This process repeats until the stack is empty. So let's start the visualization. On the screen you can see three main components. On the left it is our reference graph that shows the complete structure, and in the middle it's our working graph. We will see the traversal in action, and on our right is our stack where we show the nodes that we are planning to visit next. We start at the node A, marking it yellow as our current node, and we add as unvisited neighbors B and C to our stack. Following the DFS nature, we pop B and explore its path first. Notice how we push D and E onto the stack. We will visit them before backtracking to C. After processing the node E, we move to the second branch, that is, the stack now contains only C. C is popped and processed. F is discovered and added to the stack. F is popped from the stack and the stack becomes empty. And the final path is A, B, D, E, C and F. Alright, let's move on to Python implementation of DFS. We have our main function DFS with two parameters, graph that is usually implemented as an adjacency list, and a starting node as a starting point for the traversal. We use a stack for tracking nodes to visit and a visited a set for order of one lookup of the visited nodes. Then we add the starting node to our stack and immediately mark it as the visited to prevent the cycles. The while loop continues as long as we have nodes to explore. The pop removes and returns the top node, and we process the node. For each unvisited neighbor, add it to the stack for further processing. Mark it as visited immediately to prevent duplicate additions. So this is how we can implement DFS using the iterative approach and a stack in Python. Alright, let's move on to the key properties. The time complexity is in order of n plus e, where n is the number of nodes and e is the number of edges. And the space complexity is order of n for the stack. It is better than recursive implementations called stack overhead, and it have the explicit control over the traversal and no recursion depth limitations, better memory efficiency, and easier to debug and modify. And moving on to the applications, maze solving, connected components, finding all the reachable nodes, and the topological sorting for building the systems. So if you found this implementation breakdown helpful, hit the like and subscribe for more algorithm deep dives. Thank you.